today we're going to be talking mostly about Spark and Hadoop, right? And why these two are actually intertwined, and why it's time to say goodbye to Hadoop. So if we just look at a bit of the history, right? Hadoop is a thing that's really, really old. It's been around since 2006. It was originally introduced by Google. They wrote a white paper. Everybody got excited, say, oh, this is how we're going to be able to work with big data in the future. We're going to be able to do all that stuff with cheap boxes, and the sky's the limit, and so on and so on. And it was really the first time that you could actually do that in a distributed fashion. So that's actually a real significant event in the history of our industry. However, it was, let's say, a bit problematic moving forward, because it had a very, very simple model. Even though it was really cheap and people started jumping on it, it was really, really too simple. And the story behind it is actually MapReduce, right? Everybody probably heard of that. Well, in fact, we know those two bits in functional programming, map and reduce, as functions that we use. But back then in Hadoop, those were the only two things that we had as operations, right? And it was extremely limited, because every time you wanted to think about a computational problem, you started with the map phase, collect the data from everywhere, chunk it, distribute it, sort it, and then send it to the reduce stage to do that simple reduction computation. So at first, people started writing a lot of different MapReduce stages, one after the other, to do their computational workloads on distributed systems. But was really, really limited and clunky and awful. I don't know if some of you ever actually had the questionable pleasure of writing MapReduce jobs in Java. It was horrific. It was a soul-sucking experience, right? But that was the backbone of Hadoop. And it came also with HDFS, which was a distributed file system based on, let's say, the concept of replication and using cheap storages. So at some point, people said, this can't be the answer. Let's try something else. And that's how Spark was born, right? So it was developed at University of Berkeley, and then eventually it became a top-level Apache project. And basically there they said, let's get away from this computational model of MapReduce and try to basically say, OK, this is basically a topography of a stream of data that we compute, and we use that with a data structure called Brazilian data set, which was read-only. And I mean, all of you, and in Scala, we basically, all of this sounds very familiar, right? And the interesting bit was also that Spark was written in Scala, specifically because of the concepts that were already prevalent in that language. So essentially, it basically said, we're going to supersede all the data computational problems on Hadoop by creating a fancy framework that does that for us, right, with a directed acyclical graph for computational steps. And then we're also going to offer, to make the adoption easier, we're going to offer different high-level APIs for different languages. Even though everything is written in Scala, you also have an API for Python, even R, and Java, right? And the interesting bit, also historically, is that Spark's been a major driver for our community. A lot of companies started adopting Scala specifically because they wanted to use Spark, right? And in my experience, I personally also introduced Scala to quite a few companies just because I had Spark as an argument. So it was a good thing, right? And the other bit that was also interesting is that the folks that wrote Spark said, OK, this is going to run on MapReduce, on the MapReduce infrastructure on Hadoop, because that's the obvious choice. But we actually also want to make it possible to run Spark on different clusters. They wrote an implementation for Mesos. They had a little standalone thing, a standalone cluster. And eventually, Kubernetes also was adopted much later. And this is actually what we're going to talk about today. Spark is also interesting in the sense that it offers quite a few APIs. So there's obviously the actual Spark core API. There's also a machine learning library, which is, let's say, maybe less powerful than what you'd find in the Python world, but it has one major advantage. It works in a distributed way, which is often a problem and a headache for people using Python with machine learning. It has a graph computational API, which is not very much used, but it's there. And it has a streaming API, which is actually quite useful, specifically nowadays, where we're basically all moving away from batch-oriented, let's say, computational tasks to more streaming-oriented workloads. And also, in order to drive the adoption specifically with data science and data engineering, it also introduced a Spark SQL and a data frame-oriented API that allows people to use and interact with Spark as they do with pandas and all of those libraries that are very common in the Python world. So essentially, what also Spark also does, it also allows and simplifies connecting with different sources, right? So true to any data, my clicker just died. That's a bit unfortunate. There we go. True to a data framework that really should make it easy to connect to different sources, it basically allows reading and writing back and forth from different sources, such as HDFS, S3, Google Buckets, obviously, and with different formats as well, and also like automatic schema introspection. When you basically give it a Parquet file or a JSON object, it will derive the schema from there. It allows also stream processing from different sources, JMS, Kafka, Twitter, et cetera, and supports data stores. So essentially, what it does, it makes it very easy to solve like big computational problems. But it's not very pretty, right? So if we look at ZEO, for instance, at this conference, and we talk about pure functional programming using monadic composition, et cetera, that's not really Spark. So if you want to basically like think about Spark versus ZEO and microservices and other frameworks, CATSFX, et cetera, it's a bit like comparing a freight train with a slick, high-speed train, right? So Spark is just a framework that does the heavy lifting, right? So we really, really have lots of data, lots of different, let's say, big computational problems. You just put it on that freight train. It's slower, right? But quite effective and quite good at what it does, right? In essence, nobody really thinks that freight trains are beautiful or pretty, but they're inherently useful. So it's a different tool for a different problem. So when you look at, let's say, designing and writing pure functional microservices, and we think of a Spark, that's not what you want to do with it. You want to do that elsewhere. Hence, the differentiation between those two types of transport. So why is that, right? So what is actually specific to Spark, and why is that such a freight train compared to microservices in, let's say, in the usual other frameworks that we have in the Scala community? The thing that Spark does really well is actually dissect a job into distributed units that can be basically, can run in a cluster of, in a computational cluster that is basically managed by Spark itself. So let's say, if you think about a problem where you have a set of transformations that you want to compute, in the normal context of, let's say, a regular Scala framework, whatever you want, everything happens basically on a single node. In Spark, we have a driver that will inspect the different stages of your computation and will decide that it will, and will move those different steps of a computation onto different nodes. And will basically do the whole management of running and executing your job and running that cluster and planning also the execution automatically. That makes it very useful for those kinds of problems, right? So we have two different roles in a Spark job. The first one is the driver, right, which basically contains the, let's say, the plan of the job, right? And we're going to take this stuff from S3, we're going to do some transformations, and we're going to write that into a different format somewhere else, right? So that's, let's say, the job. And the driver will then interact with whatever cluster management we have, usually Hadoop, right? As I say, I'm going to run this stage on a different executor node. And I need a worker node from you, and that worker node will then get this computational unit and process it. And what Spark also does is also checks and verifies that those computational stages have been executed. So in essence, if the driver notices there has been some kind of failure somewhere, well, we're basically it's going to stop that computation and restart it. So you have also the driver and Spark are capable of checking different stages and reapplying them until basically they get executed. So there's a lot of, let's say, fail-safe mechanisms, which are like historically come from Hadoop. Hadoop did the same with MapReduce, and Spark basically copied that approach. So the interesting bit is that you basically get a distribution model out of the box for free, almost for free, let's say, when you actually run Spark. You don't have to bother about distribution. And so for each stage, Spark will plan the execution of your job, will ascertain that it completes, and then will pass on the next stage to the next worker node. And it is also quite clever in planning, let's say, sizing, right? So if you have a chunk of data, a partition that you're reading from that does not fit into memory, it will basically automatically spill over into disk, so that it can basically then be read by the next stage and processed. So essentially, what it also gives you is the ability to run and process large amounts of data that do not fit into memory of a single node. So in a nutshell, right, Spark makes it very, very easy to work and reason about like distribution and data sourcing. So really, really very simple. It just says, okay, these are the types of sources that I can use, like Cassandra, Kafka, S3, buckets, HDFS, even flat files. And I want to write them somewhere else. I want to do transformation. I want maybe to also apply and train machine learning models. All of that is fairly simple because the whole, let's say, heavy lifting is hidden or basically taken care of by the Spark environment. The drawback is, I mean, inherently, it's not pure, right? This is basically functional OOP, right? So it really resembles a bit the handling collections in the old Scala APIs, right? You just have collections and you just work with them and you do transformations using like those API functions that are very, very familiar when you basically look at them. But it's full of effects. There have been some attempts to integrate frameworks into Spark that didn't really work out. That's why essentially, as a Scala programmer, when you say, okay, I'm going to write a Spark job, I'm going to have to endure the fact that I cannot actually do all the fun stuff that I really like to do in let's say, in pure functional programming. But that's fair enough because Spark is inherently useful for very specific jobs, right? And it's really, really good at runtime optimization. And it's obviously vastly superior to MapReduce, but that's actually not a surprise either. So that's essentially Spark. And if we now think about runtimes, right, we come back to Hadoop, right? So, and those two, Spark and Hadoop, have been in a symbiotic relationship ever since, right? Most deployments of Spark run on Yarn clusters. Yarn is the job executor of Hadoop, right? Hadoop is essentially, let's say, not really a product and more like a family of tools, right? And so most companies run their Spark jobs either on an on-prem cluster with a Hadoop distribution such as Cloudera, and et cetera, or they run that in the cloud in the specific Hadoop managed service environments that exist, be it EMR or Dataproc or HD Insights in the different cloud providers. And the reason why that's done is that obviously the cloud providers give those managed services and try to take the operational hassle of running a Hadoop cluster away from the users. They do that quite well, but it's still a pretty complex system with lots of moving parts. HDFS nowadays, which was like the venerable distributed Hadoop distributed file system, has been largely replaced by buckets, right? Be it S3 or the blobs or GCP buckets, because they also behave pretty much like HDFS as object stores. So essentially, nowadays, it's really just about Yarn, running Spark jobs with Yarn on a Hadoop cluster rather than using most of the tooling that came with Hadoop, because we have those cheap object storages in the three and other also cloud providers. So what usually happens is that users also either have like standing clusters and run their Spark jobs on them, or they even actually say, okay, I'm going to ramp up a cluster, run my job, and when my job's done, I'm just going to basically destroy it, right? All of that is actually quite costly, right? A standing cluster costs a lot of money, right? Because obviously you have like all these boxes, or ramping up a cluster also costs money because you also have to wait for the cluster to ramp up. It takes time before all those instances are up, and then you can run your job, and you have to wait for your job to finish running. So if we look at the pros and cons, right? Obviously, this stuff's been around for years, so it is really rock solid, right? Hadoop is old. It's like 17 years old. And everything has been seen. There's a lot of support and a lot of knowledge about how to run clusters, how to run them. And obviously, the public cloud providers really know well how to run those, and they're rock solid. However, and another pro is that you have a lot of additional tools that you can run on your EMR cluster in conjunction with Spark, be it Hive, which is essentially a SQL interface on top of Hadoop and HDFS, or Zeppelin, which is an integrated notebook, so you can actually run like interactive queries using Spark like a bit like Python notebooks. And of course, as I said, you have really good managed support for GCP, AWS, and Azure. But the cons, right, is it is a heavyweight cluster. It runs on each instance. Each worker is a VM, right? We're not looking at containers here, right? We have to ramp up clusters. It takes a lot of time until they're up and running. It's siloed, and that's actually the biggest problem, because EMR is just that, EMR or Hadoop generally is just that one cluster type. It just runs there, and it is not integrated in the rest of the application landscape. And lastly, the Spark version is tied to the cluster environment that you're running on. So we want to get rid of that, and that's where Kubernetes comes in. So the cool thing is Kubernetes has been around since Spark 2.3, and it's now fully GA. It runs in two operational mode. The one easy way is to use Spark Submit, which is a script that runs as part of the Spark distribution. You just say, I'm going to target a Kubernetes cluster, and it just does all the packaging for you. It creates a Docker container, deploys your application, submits it, and does all the coordination. The better way now is actually using a Spark operator, because it's super flexible, and it's actually the Kubernetes native way of doing things. So if we want to have a look at those two specific operational mode, as I said, if you use Spark Submit, it just packages the application, executes the driver and the executors in the pod, and does all of that for you. It is really easy, but it also assumes the default permission node types that are available in your clusters. You do not have that much of a customization. But it runs out of the box. So for the most simple cases, using Spark Submit, if you just want to try it out, it's fine. It just works. The interesting bit, and that's what we're actually advocating, is using the Spark operator, because the Spark operator gives you the ability to define custom resources. So you can basically say, specifically to the application, I want to have these permission sets, these roles, these types of instances, Especially if you have a machine learning application, you could say, I want to specifically select GPU worker instances for my containers. You have a fully declarative approach to application specs, right? You can configure your own restart policy instead of just basically using what is the default in Spark. And you can also map volumes, configure pod affinity, et cetera. So you have like full control over the runtime behavior of your application. And lastly, and that's actually quite important in terms of security, you can configure specifically profile security with service accounts. Right? So instead of relying on whatever is defined for the entire cluster, you can say this application has exactly those permissions, especially in cloud environment, where you want to say, you run a Spark application, you want to say this Spark application can actually access exactly that bucket. You can do that using instance profile security. And also cool is, as a big change compared to Hadoop, you can specifically say, I want to run this Scala version and that Spark version for this application, run different versions in parallel, as opposed to basically having to use whatever your Hadoop environment gives you. So generally, it's running Spark and Kubernetes just gives you that same ecosystem as your other microservices. You can run that on the same cluster. So there's more interoperability and more integration. You don't have to basically say, OK, the Spark application runs on a Hadoop cluster. We have a completely different operational environment, and our microservices run Kubernetes. You can integrate all of that. You can test your Spark apps using containers, which is a big, big hassle otherwise. And as I said, running different Spark versions, and specifically Scala versions, if you want to use 2.13, that's fine. That works with Kubernetes. And specifically, fine-tuning runtime behavior and security is a big plus. So obviously, the advantage of you running Kubernetes is obviously portability. So if you run your Spark stuff on a Kubernetes cluster, you can just move to another cloud provider, because Kubernetes is basically the de facto standard for containers. And lastly, it is much cheaper to run. We usually see cost savings of roughly 20% on AWS if we move an application from Hadoop to Kubernetes, just because it's much cheaper. You don't have the overhead of running the EMR cluster. You can use containers, utilize resources more effectively as well. So generally, there's a bit of work to be done because it's relatively new, so the tooling has to be improved. The community is working on that. And the big advantage of Spark, the dynamic allocation of jobs, which runs really well on Hadoop, is not quite there yet because, let's say, there are some very, very specifics of how Kubernetes plans and allocates resources that need to be reflected in the Spark framework. So in a nutshell, it's really time to say goodbye to Hadoop. Thank you very much for all that time and support that community gave, and it's now time to say hello to Kubernetes. Thank you very much.